Joe has limited time.
Okay, yeah.
So he's going to make some comments. I think there are a few other people who would like to make some comments, and there's probably other questions.
Good. So yeah, I have to leave, unfortunately, for a faculty meeting in 15 minutes. But I wanted to comment on the most interesting difference between Dan's talk and Vladimir's, which actually didn't come out in the talk or the questions. But it's that Dan's approach has significantly extended potentially the reach of the whole precursor construction. So let's consider, again, the CFT. Let's break it into three regions. And these comments are expanding on something actually that's said in Harlow's, in the Happy paper, Harlow, Pestowski. Let's break it into three regions, but let's erase. Let's not have, let's make little gaps between those three regions. Now, if we didn't have this gap here, then in the way that Vladimir described, the conventional precursor construction, which is what has been developed, in the course of 15 years by many people, including, as we heard from Dan, Kabat and Vladimir, you could construct this entire region if we had this boundary region. But as soon as we lose this little bit, then we can only construct this much. And the reason conventionally that this is true is that the operators that we thought we needed to build the larger thing involve Wilson lines that stretch from here to here. Because the construction that Dan and Vladimir described essentially will generate operators like this. And as soon as you lose this gap, you can't measure those Wilson lines. It seems as though, at least from a conventional point of view, you can measure much less information about the quantum state. And in particular, this is in the toy Z3 site model that Vladimir started with. This is true. If you can measure only gauge invariant operators here times gauge invariant operators here, you cannot measure the point in the middle as he constructed it. You have to be able to measure the analog of Wilson lines, gauge invariants that stretch across the two regions. Now, those of you coming from the entanglement tree community say, no, we're sure we can construct the whole entanglement wedge, this larger region. And this is really interesting because in the approach that Daniel described, say in his three-site model, this is true. If you can make local measurements here times local measurements here, and from those local measurements and correlations of local measurements, you can reconstruct the state in this larger region. So if this new thing is true, it's really an extension of what we thought of a precursor as to something which goes much further. But also it changes very much how they're built. In fact, so again, there's this formula, the smearing operators and so on, for the precursors in this region. And there's no formula for the precursors here. And it's going to have to be something kind of weird, because we can the operator that we can construct a precursor operator that creates that part that excitation there, and let me run the dressing down. Don't worry about the dressing for now. Let me run it down here for the sake of this argument. And this operator commutes because essentially of bulk locality. The precursor operator construction guarantees that this commutes to all orders in 1 over n with gauge invariant operators here and with gauge invariant operators here and with products of gauge invariant operators here times gauge invariant operators here. It's only when you add in the Wilson lines that cross it that it wouldn't commute. So you have this interesting thing that you act with this operator, it creates an excitation. It has seemingly a very subtle effect on the density matrices in these two regions. It doesn't affect them in some sense to any order in the large n approximation, yet there is some measurement that you can make that sees that. So anyway, I think this is the real difference between the two talks. And if this is true, it would be, well, again, if this is one.
Just to be clear, the measurement is that there could be entanglement between A and B.
That's right. That's right. Right. So right. So, I mean, you want to say your one. Yeah. You're right. So Vladimir's one word was gauge invariance, and your one word is entanglement. Right. That in fact, if the proper entanglement exists between A and B, then and so I mean I think this question how you rectify your point
if the proper entanglement
between A and B, then in fact by local measurements in A times local measurements in B, you can measure this larger region. So the question is really how you reconcile this new point of view with A with the inability to measure the Wilson lines and B with the large N approximation. But if it's true, it really moves forward this idea that space-time comes from entanglement. Anyway, that's all I had to say.
Let me just ask, so if you had the reconstruction from the undisturbed causal
Yes.
wedge of
Yes.
A and B together,
Yes.
so you would have gotten your operator in the center from the standard reconstruction, and then took that density matrix and did some operation to somehow passively.
Wait, sorry. Could you say the first part? I misunderstood. Say the first
So
part.
take the A and B without the excision.
Take the full one. Yes.
Take the full one.
Yes.
Reconstruct that operation.
Yes.
I want to ask, is there some way to somehow very mildly remove the
it,
point
right.
between A and B that sort of, even though you don't know about what's there, you know that it's not going to be something so drastic as to sort of, destroy somehow all the...
I mean, you want to say one?
Well, actually, in gauge theory,
Yes.
you can do something like this, right? This is, where's Will? Well, has looked at this. That you could take a Wilson line there, but then you could break it up and put surface charges on and
Right. So the question is, I mean, is there a sense in which this Wilson line times that Wilson line
with some correlation
is a good approximation? This might, in fact, be the right way to think about it.
I mean, actually, so thinking about the thin
Yes.
Wilson line, I think is probably not the right way.
Because it's not the true, yeah.
Because the degrees of freedom are already delocalized.
Right.
And your race to do the thing is not.
Right, good. So you say it's, I don't know how you want, yeah.
But you
Yeah.
might hope that because it's delocalized,
Yes.
removing one little point
Yes.
will make a whole lot of difference, which it does in this study. But is there anything one can do to not make a whole lot of difference? Have a large Wilson loop and then just remove one point from.
So do you think if I have two Wilson lines with where they end on quark and anti-quark pairs?
Yeah.
And I bring the quark and
Good.
anti-quark very close together.
Yes.
And I smear the operator. a little
Good.
bit.
correlate.
So I mean, if you turn on a little bit of time evolution, this operator will turn into this operator. Oh, that is suppressed in the 1/n approximation. That is the reconnection or splitting interaction costs you a one. So somehow.
You're supposed to rescale though to get finite low energy.
Yeah, right. If you rescale, okay, good. If you rescale, but then there's the disconnected pieces which you've now scaled to be huge. So somehow they have to be suppressed by something else. In fact, maybe that's what it is. Maybe you take this times this, and the disconnected pieces take you out of your code. I don't know if that's the right word.
Yeah.
But you want your precursor. You want your precursor to leave you in the code subspace.
It's right that the general disconnected pieces are breaking the original.
No, I think if you smear, then you kind of remove the high energy part of the operator, and then you rescale.
Smear in time.
Smear in time. Yes.
You want to effectively smear in time. Will that do it? Will that pull it out?
I think so.
Okay. That
Seems like
Possible
I don't
construction.
know. I don't
Yeah,
have a proof
yeah.
for you, but
Yeah.
it seems plausible.
yeah.
This operator where you add the quark anti-quark pair, I mean, that would conventionally not be an operator that's not a gauge invariant operator in A cross a gauge invariant operator in
No,
B.
yeah, it is. That's what the whole point was to do that. Yeah.
If you have quarks in the theory.
If you, of course, yeah.
Oh yeah, but you
You
have very
might have to
massive
introduce
force.
new degrees of freedom if it were
That's right.
pure entanglement.
So in the original theory,
Yes.
the thing you were saying is true. You had this big Wilson loop, which
Okay.
was gauge invariant in the original theory, in the AB region without the hole. Then you put the hole in,
Yeah.
and you have no candidate operator. That's until you add extra degrees of freedom.
Right. But the real theory has stuff floating around it.
I mean, I think I could also just put in very massive quarks that are irrelevant for the rest of this discussion, and then by doing the smearing, in time I could project back back onto the low energy Wilson line without,
Good. You say you can kind of your definition of your operator can include such massive quarks in effect, right?
Yeah, I think in the UV I can put whatever I want, right? I mean,
But then is that different from
But you
extending a set of allowed gauge configurations to have some similarities?
Yeah, you're really extending the Hilbert space theory
Yeah.
in a non-trivial way.
yeah, but then by doing the smearing, I fix it.
You project back down.
Yeah.
This is a question of UV completion, UV
Yeah.
sensitive. Shouldn't be a UV sensitive question.
Right. Yeah, that's the intuition. I can use whatever UV
I mean,
completion I
to
want.
divide the system into two, you are putting some surface charges in place plane.
Yeah.
Right.
Yeah.
Just surface charges.
Right.
Someone else want the microphone?
Any other questions?
I have a question for everybody. Okay, which is, I'll use the blackboard to do one thing. I don't need the microphone.
We can hear you over here.
I just had a question. So let's take the ADS3 case just to be concrete, okay? And let me try to, there's been all this discussion about fields in the ball commuting with local operators in the boundaries. I want to ask about non-local operators. And I just asked an expert, at least for an opinion, on whether if I take a local operator in the bulk, it should commute with a large Wilson line on the boundary. And I want ADS3, where a time slice can be sort of covered up with a Wilson line. But I want my Wilson line, just for the sake of argument, to sort of go like this. Here, this is, the blackboard is the boundary of ADS3. This is a time slice. It's global ADS3, so it's periodic. And I want my Wilson line to do this. Okay, and why do I do that? It's so that I can gravitationally dress this thing so it ends there. Okay, and then my question, but I asked an expert about whether this local operator should commute to all orders in 1 over n with this Wilson line, and the expert said yes.
Did he sigh?
What's that? I don't know whether everyone in this room is immediately going to agree with my expert, but let me suppose that it's true. Okay, all right. And my question is, do either of the models discussed reproduce this? Because there's a lot of discussion about the models giving this thing commuting with local operators, and to the extent that I could write this using HKLL as something that lives on some, moderate-sized subset, it tells you it commutes with certain Wilson loops. But there's no way to use HKLL to map this operator into this small region, so it's not immediately obvious that this commutator is satisfied. And I'm curious whether either model does this, or both. So that's my question for everybody.
Not manifestly. Certainly.
Not manifestly.
Are
Okay.
you sure it commutes with that? Are you wait? Are you sure that it commutes with that big loop?
Well, I knew there'd be a discussion about that, so I tried to head this off.
So what is the argument? Expert.
Well, okay, so I asked one.
Have you done this once with other people we know? Or at least a related people?
Don't you want these kind of narrow wave packets so it only hits that boundary region, or you want the isotropic?
Sorry, wave packet for what?
The boundary, the thing in the center. What's in the center?
It's a point-blank local operator dressed with a gravitational Wilson line.
I don't think that has non-zero commuters all around the boundary. I mean,
No, not in Featherman Graham, right?
no, it's not the Wilson line that's the issue. It's the operator itself. It can move in any direction.
Sorry, I mean, using the bulk field theory argument, it certainly commutes with the boundary values of all local bulk fields at this time.
But
Yeah.
Okay, and the question is whether it extends to stringy things. So I'll let someone else comment.
I mean, think of this Wilson line as coming from a gauge theory in the bulk, right? Let's imagine this string not as the string of fundamental theory, but let's imagine there is a gauge theory in the bulk, and this is some string, and then this is an ordinary local operator in the boundary theory Wilson line. So the same, but I mean, the usual bulk argument would imply that they commute.
I think
And
it's
then-
related to the, long ago, Lenny proposed that the precursors were the Wilson loops, the smooth Wilson
Well,
loops.
I insisted a moment ago that we should not think of them as very thin, and I think you really want to spread them in time so that they are more non-local. I mean, just think of this as not a fundamental string, but the string of a QCD theory that lives in the bulk.
No, but what I
Then
was going to
the
say-
standard.
What about the string that lives in the boundary? That's not the same.
No. Okay, so take a QCD theory, right, that lives in the bulk, and make this a Wilson line operator very close to the boundary, right? So from the bulk point of view, this should commute.
But on the boundaries, you say it'll be smooth.
No.
No, it won't. Oh, I see.
No, it's just localized, as Don said, to a very narrow region in the boundary. Presumably, if you smear this over a region of size of order pi and so on, of order the size of the circle, then it might reach into the interior. That's what one would expect.
But also, if you sort of fill it out with a string world sheet, if you think about it in string theory, I think there's a similar calculation.
Similar to what?
Similar to what you just said, that shows that you get that it commutes.
Yeah, so the string will end. I mean, when you create the string, it will just go into the bulk along the light cone, and
Well, here it goes in and comes back out, but that's a timeline. That's the top and bottom layers.
no, in the sense that you create a pair of string and a string that might annihilate in the interior or whatever, but their effects will be restricted to the future light cone.
Right. Yeah.
Is there a reason why you didn't talk about having it just be the fundamental string using the usual rule for interpreting this Wilson line? I just didn't.
The reason is to use the bulk expectation just to connect it to some other thing that we knew about the bulk. That in the case of a QCD string in the bulk, we expect it to commute. And then one would expect there shouldn't be any difference for the fundamental string.
Right.
Just because you could say, well, for the fundamental string, what is exactly the rule for how the...
Probably even if it's a fundamental string, maybe you think it commutes, right?
I think so, yeah. But someone could say, well, maybe it doesn't commute, but the non-commutation is suppressed by e to the minus lambda, which is the action.
We basically had an argument in the case that Lenny was talking about long ago that it did commute. I'm trying to remember what the Ben and I and Matt.
Yes, I'm sure that extrapolating that argument to this case would say it commutes.
Although neither of us seem to remember the details.
No, it's not. Yeah. I mean, is there something obviously wrong with saying this Wilson loop? I mean, certainly your QCD case is correct, okay? But in the case that we're talking about a fundamental string, there's something obviously wrong with saying this Wilson loop operator in the CFT corresponds to an operator in the bulk that creates a string whose world sheet ends on this
What's wrong with
boundary region, right? So I think someone has made that statement before, but that's a corresponding bulk operator. If that's the bulk operator, that bulk operator creates a string world sheet that is not just localized at the boundary.
Okay, yeah, we shouldn't think of the operator creating the Euclidean world sheet, the minimal area surface. The operator, I mean, if you think as a physical source operator creates a string that then will move.
Well, we'll talk about a space like Wilson.
Yeah, space like Wilson. Well, it's the same as if we act with let's say we act with a pair of operators at these 2 points, right? We can compute the expectation value using a Euclidean world sheet that goes between a Euclidean world line that goes between these 2 points. But when you act with these 2 operators, you don't create the Euclidean world line. You create 2 particles that move forward in time.
That's right. So there you're talking about a time like Wilson.
No. Here
You have
the
these two
insertion
particles
so the
on the
analogy is between the whole space like Wilson loop and the insertion of local operators at 2 points.
Yes.
So in the case that you insert space like Wilson loop, you'll create a world sheet that will start moving in time, not the one that moves in space.
It's not a precursor for a string deep in the bulk.
Yeah.
No, obviously.
It's just a source on the boundary.
The leading order thing that we'll do is we'll create the string.
It's a source for the classical string propagation.
I mean, the idea is this things deep in the interior have to do with very low energy modes on the boundary theory. I guess that's fairly clear in this tensor network description. But and also from the RG and always discuss this.
So this string world sheet in the bulk, which is moving in time, would that be space-alike to the boundary Wilson loop?
No.
No, it's called the source. It's sourced by it.
So it obeys bulk causality perfectly.
Yeah, that's what one would expect.
At least in our sense, as you say.
Yeah, well, well, if there's a bulk.
It is called.
So this exactly. Then I have another question. And also, I think, Ben had some comments possibly, but maybe go ahead.
Well, mine takes up a new angle and everything about entanglement in the CFT. So if you're more along the lines of what we were just talking about.
Can I maybe make one more comment about this first? So I think Don is getting into something non-trivial here, which is that all of the arguments we've been making, we're trying to make them in a strongly coupled CFT. And so the only tool we have available to us is commutativity and space-like separation in CFT. And Don is giving an example of something where, so with the local operators, I always was able to use that to argue that these commutators are small by arranging for the boundary representation of the operator to be space-like separated from the operator I wanted to show that it commuted with. But here, since Don is using the entire boundary, that's not a trick I can use.
For almost all of it.
Yeah, almost all of it. So this is not a thing that's manifestly true in the way that we've been thinking about things, which suggests that there's got to be more than just what sort of manifests in tensor networks.
So Ben or Ed, whoever wants to.
I have some very general question. These constructions assume that there is an embedding. There is an embedding of the bulk Hilbert space into the boundary Hilbert space. And if this is true, then one could try the following thing. One could map states in the bulk to states on the boundary in two ways. One way is to create a state by a bulk operator, propagate it not sideways, just backward in time until it hits the boundary, and it kind of dissipates at the boundary. So if we move this long enough, then we don't need Koch data in the far past. This will be a state on the boundary. It can be evolved forward in time to time zero. And one can do the same, propagating it first to the future and then moving back. And if everything is consistent, then we should get the same answer. Can this be verified explicitly in some model?
Well, these guys had a paper about this.
He didn't do it explicitly in some model.
Yeah, he didn't do it
although the
explicitly.
model that Vladimir presented this afternoon should do that, because it's really just consistency of the bulk and boundary equations in motion. So I think it's clear that it's true in the model that was presented in the last talk.
Yeah.
That's all this?
It's equivalent to the statement that the bulk and boundary dynamics are consistent, which I was told was true.
No, I'm serious. Because, this intuition may not be applicable to the standard ADS-CFT. It's applicable to black holes. So I came up with this question by thinking how the Hawking picture of black hole radiation breaks down, why it breaks down. And it breaks down for the following reason. it's not even specific to black holes. We can just take a lump of matter that radiates, some complicated object. This is a quantum system. It has some Hamiltonian. However, we can consider it as an effective heat bath that is kind of Gaussian, it's an approximation. This approximation is actually very good. It can be very good. In this approximation, we can try to build a Hilbert space. Actually, it is a Hilbert space already, this Gaussian model. And we can try to build an embedding into the Hilbert space of the true model in the following way. It's basically the GNS construction. We take some operators. We can act by those operators on the true model or on the effective model. This will give us states in both cases. If the correlators agree, then we get embeddings of Hilbert spaces. However, in the effective model, we cannot actually compute all correlators. We can compute time-ordered correlators or reverse time-ordered correlators consistently. This builds two different embeddings of the Hilbert space. And this can be fixed at short times by adding these shock modes as new degrees of freedom. In this bigger Hilbert space, both embeddings are consistent. But I'm not sure if it will hold for longer times. So eventually it might break down. So I'm kind of prepared that there is no full correspondence, no consistent theory. It consists only to get to solve certain problems. But that's why I'm asking.
Well, I mean, I think in Don's paper with Joe and Jamie Sully, they gave a way in which this would work. I mean, they suggested a way in which this would work, right? I mean,
you said it's not inconsistent.
Yeah. There's no. Yeah. I mean, there's a way. You know, I mean, whether or not that's actually how it works, I mean, it seems plausible to me. But yeah. I mean, well, yeah. I guess so. Probably since I like ADS CFT, then I think it works that way. You know, where you're careful to only define the interpretations of operators with respect to a fixed time and boundary. And you want to have the physical interpretations of operators in the Hilbert space of the theory be independent of whether or not you turn on sources at other times.
That's a different issue.
Well, no, because these shock waves are sources, right? So I thought.
No, I meant the following. We have two different embeddings. One uses time-ordered correlators. The other uses anti-time-ordered correlators. Let's try to reconcile them and build an embedding that uses all possible correlators, regardless of order. To do that, one can. It's done in an effective field theory where we have some free fields, bosons or fermions, and a pair of shock waves. If we couple fermions or bosons to the shock waves, and those shock waves are just like an inverted oscillator, the Hamiltonian is x times p. X and p are canonical variables. The bosons are coupled to that. Then it seems consistent, but on the other hand, the system is unstable. It tends to break down. So I don't know how well it works at longer time. But I mean, the shock waves are necessary to build the full Hilbert space of the effective model.
You said you're evolving back, and you're using retarded. So you said you evolve back, and then when you go far back, then it decays. So are you using majority Boltzmann? Why is it decaying quantum fast? Is this point quantum fast is time like separated from the bulk line? So what's decaying?
So I think the instruction is you start with a given wave packet here, if you will. You evolve backward to sort of outgoing boundary conditions that flow out into space.
That's what it is, though? Is that what you're doing?
Yeah.
And you use that to read off what we would call a source that you could then get back to create the operator when you time reverse this process.
Okay.
Yeah.
But again, in your model, you wrote down the free field linears and the boundary, and then you construct this O, which is phi dot phi, and you tell me that it does satisfy the free wave equation in the bulk, and you do order in one over n.
Yeah, that's
So then once
the
that's
case.
checked, it doesn't guarantee that this works.
To the leading order of 1 over n, but then it might be multiplied by an exponential factor.
Right. Okay. Yes.
Other comments on that?
I just had a question. So, am I right in thinking of what you just said amounts to asking something like a fluctuation dissipation, holding at arbitrary times for you to be able to get the noise correlations? Or am I missing something?
I'm talking about four-point function, and all corrections are of the order of 1 over n. In the normal 4-point functions, these corrections stay small. But with reverse time order, they're multiplied by an exponential factor.
Ted, so was your question about this whole error correction circle of ideas, or more broad?
Yeah, it connects to that.
Okay. So, well, whoever. Okay.
So I just wanted to hear more about, I think that we heard, and maybe it was in Dan's talk, that it's important that the CFT has long distance entanglement in order for bulk reconstruction to make sense or work out the way we expect. So I just wonder how much is understood, if anything, about long distance entanglement in a strongly coupled CFT. Like, could you ask a question about the mutual information, between regions separated by a certain gap size, and then look at how it scales with that gap? Is it comparable to the entanglement across, just a plane, quantitatively, or what do we know about that long range entanglement?
In 2 dimensions, in 2 dimensions, that particular question has a nice answer. It's just it's basically the 2-point function of the lowest dimension non-trivial operator. So there's a general bound on mutual information, which is if you look at the mutual information between 2 tensor factors, then if you look at the correlation function of the connected correlation function of any 2 operators on, say, region A and region B, then that gives a lower bound for the mutual information. You have to normalize the operators by their, say, largest eigenvalues. And so then you can show, for example, in 1 + 1 dimensional CFT that's saturated by this lowest dimension. I think Juan showed this in the paper. Maybe, I don't know, maybe Matt Hedrick did somewhere too.
This is when they're separated by a long distance.
Yeah, when they're separated large compared to the size of the regions. I thought that's what you were asking. When the separation between the 2 intervals is large compared to the size of the intervals.
Yeah.
Yeah, so that's when this is true. Yeah, when they get closer, then other operators matter too.
So what does that work out to quantitatively if you compare the amount of entanglement entropy, let's say, between such regions versus the amount UV regulated just at a boundary?
Well, that's what's nice about the mutual information is it's finite.
It's UV finite.
Right.
But then I think that perhaps what you're asking is if you have 2 regions that are close, then the mutual information goes like 1 over the distance. It goes like 1 over the distance to the power d-2. So it has the same behavior as the regulated one, but where the distance is the regulator. Right. Is that answer?
That's quite true.
This is true for any theory theory.
That mutual information it diverges as you make the intervals close to each other, and it's also proportional to n squared, the large n theory. So if you take the intervals and make them far from each other, then the mutual information is of order 1, and it's decaying like the square of the slowest decaying 2-point function in the theory. So it's a very small. The mutual information is very small compared to 1, as opposed to both divergent because the intervals are close and proportional to n squared. It's extremely different.
Yeah, there's a phase transition at some distance where there's a jump of this mutual information being in further n squared to being in further 1. That's something special to strongly coupled large n theories. Well, maybe it's something special to large n. Yeah, maybe the phase transition also happens in weakly. Well, no. I think it's special to strongly coupled theories.
This entanglement wedge issue is about when the information is order n squared. Right? That's when you can do something new.
Right.
That's correct. Right. That's somehow the place. So the n squared seems important.
Yeah, the n squared means the bulk is connected somehow.
Yeah, but in a CFT, how do you? There's no scale, so how do you decide at what distance you transition from n squared to 1?
The size of the region provides the scale.
There's the separation and there's the size of the region.
There's some measure of
In 1 plus 1 dimension, there's a cross ratio, which is following that. 1/2 is the critical point.
Anything else on that?
Yeah, okay. I had a all right. I wanted to make a comment about Rendler versus global reconstruction. And my point is just that I think there's something qualitatively different about reconstructing the bulk Rendler wedge from its boundary versus reconstructing from data on the entire boundary. And I think there's some things we know about this. I can tell you the simplest thing that we know, but I don't think we understand the physics of that fully, and I think it should fit into these stories about, these stories use this Rendler wedge reconstruction a lot. And I think that kind of the math subtlety that we know about here, I think we don't have the full physical interpretation, and I think, something like error correction, gauge invariance, something about the UV properties of the theory should come in. So to define, here's ADS, here's time, and if you take some Rendler type coordinates, then we have this right Rendler wedge over here in the bulk. And we have its corresponding boundary region like that. And the type of thing that was going on in these talks is that we think, ADS lore tells us that if you have a point, this drawing is not up to the standards that some people have set here. But if you have a point that's in this bulk Rendler wedge, we think that you can reconstruct it from data on the boundary Rendler wedge. But there's something that's different about this reconstruction, and I just wanted to mention what that is because everyone has glossed over it, and I would like to understand it better. And this difference shows up already in the simplest case. So the simplest limit of reconstructing the bulk is when we take weak gravity and things are classical in the bulk. Okay, so we're just looking at a classical bulk. And we're doing weak gravity, so we can just say we're solving this equation in the bulk. And the way I would like to phrase the question is that what we want to do is we want to reconstruct the bulk solution. So somebody put in a normalizable bulk solution, but they didn't tell us which one. And we want to reconstruct the bulk solution everywhere from the CFT data. Okay? So one way you can do this is essentially the thing that Dan was telling us. If you want to know the bulk field at some bulk point there, you just take the boundary regions And you can focus on a particularly simple class of CFT data, which is local CFT operators. And those things are dual to, after some rescaling, limits of bulk fields. So this is a particularly simple class of CFT data that we actually understand the bulk dual of. And so then you're just solving a weird boundary volume problem for partial differential equations. You're trying to solve this equation with some boundary values, phi at r equals infinity and x mu. Those things are given because those are dual to CFT operators. You're given your CFT computer, and so you know those boundary values. Okay? So that's a weird PDE problem, but it's a problem in PDEs, and you can solve it. Dan solves it explicitly for this problem with his collaborators. And so then, at least in this limit, you have this very simple correspondence. But this simple correspondence, so you can ask the same question just in Rindler. You're doing exactly the same thing, solving a classical wave equation in Rindler, and trying to reconstruct the bulk field value there from the boundary values. And my claim is that this thing is qualitatively different. So in this case, you could write, of course, a formula which said that phi bulk at some point is some kind of integral involving this over the entire, over a space-time region on the boundary of some smearing function times these boundary value of phi. Now, in this case, in this Rindler case, you can write some formal expression for the smearing function, but you can't actually write a formula that looks like this, that has a position space function here and a position space function there that depends on the position space location of this point. Okay, and the thing that, so in that case, there's only a formal expression for k. Then the thing that's not clear is what's the physics, but I can tell you what this means from the point of view of partial differential equations. You're trying to solve this bulk equation, and you're given the boundary data over here, and if you kind of steal a math theorem, then what it tells you is that, in fact, in this kind of situation, there's no continuous mapping from boundary data to the bulk solution.
Is there, if the boundary data comes from,
it
can't be general boundary data.
It's your notion of continuous that's up for debate.
That's right. So this.
Namely, what boundary data is allowed?
Well, what's your notion of continuity? On what space are you measuring?
What do you mean?
That's right. No, that's right. So
that's right. But boundary data is not arbitrarily chosen data, like initial data would be in the Cauchy problem.
No, that's right. So
there is a set of boundary data for which I claim you can define some continuity. But I agree with you that the smearing functions do not invert the classical Cauchy problem. The smearing functions in the literature cannot reconstruct what I would consider arbitrary initial data in the bulk. It's actually more special data.
That's right. So the point is, this is telling us something.
No, in global it inverts the Cauchy map. That is
Actually,
there's some issues.
Hold on, you can specify any data you want, but you get a non-normalizable solution.
In the center, you mean?
But yeah, if you specify any O on the boundary, smear it with a K, you get a non-normalizable phi.
So can I pause to ask a technical question, which is how that observation, that I think I agree with, is consistent with the implied converse here, that in global IDS the map is continuous. So what notion of continuity is being used in the bulk?
So I think the statement, the way that the question where these things are different is that now this boundary data here it's true that if you're solving the bulk equations, which in this case means solving the bulk equations in a normalizable way, then this boundary data can't be any old function. Okay? So the thing that's true is choosing allowed boundary data. Okay? There's a continuous mapping between allowed boundary data and allowed bulk solutions. Okay? In the sense that...
What is allowed? What is the...
Normalizable.
Well, in this case, so for example, in Poincaré, for example, that is where something is particularly simple. You can answer the question.
Yeah. Okay. He answered.
Okay. Okay. The answer is there's an answer, but it's a secret. Okay. The answer to the question is that. Yeah, but for example, in Poincaré, on the Poincaré boundary, the allowed boundary data is only allowed to have Fourier components where omega squared is bigger than k squared. Okay, so you have a constraint like that, which is a pretty big constraint on the allowed boundary data. Then if you have boundary data satisfying that, then there'll be a mapping from the boundary data to the bulk data, and it will be continuous in the sense that if the boundary data is close to 0, the bulk solution will be close to 0. Okay, and the case where this is true in many different norms, but the point is these norms are some local functions of phi. So the norms for defining by what you mean by small boundary data is things like integral over the boundary of I don't know di phi squared, for example. Some kind of local function on the
that
boundary.
condition that omega squared is larger than k squared,
Yeah.
it also is a bulk interpretation, right? Those are the modes that don't blow up at the Poincaré horizon.
Yeah, that's right.
So you didn't have to specify.
No, that's right. That's right. So there's no mystery here. My point is that there's something different about this math problem than that math problem. Okay? And yeah?
But one clear difference is that one, the one on the right, is sort of unique region on the boundary, which is just a set of space-like separated points from your bulk point, which is just unique for the given bulk point, whereas on the left, that's very non-unique. So there's a big redundancy that's built into the thing on the left.
Yeah, that's right. Well, at the moment, I was talking about a point that's inside this wedge. So in fact,
it could have been any wedge, whereas that one, there's a unique set of space-like separated points once you're given a bulk point.
Well, he could have done the Poincaré patch though, and then he can rotate the Poincaré patch around, and there's some.
But okay.
Yeah, so the Poincaré patch.
But the Poincaré patch is good
where
according to his rules.
But okay, there are many differences. Oh, so one thing I should say, since I mentioned that this boundary data is restricted, this boundary data in the Rindler patch is actually arbitrary. Okay, so that from that point of view, it's simple, but from the point of view reconstructing the bulk solution, it's complicated because there's not a continuous mapping. Yeah.
So just once I mistake everything. So the distinction is at the level of modes that in ADS Rindler one has modes at any momentum, at any transverse momentum k. One can have the frequency of the mode be anything, including omega less than k.
Yeah.
It's sort of consistent with energy conservation because the energy is measured at the boundary of the energy redshift. And so these modes with omega less than k, they only exist in Rindler, they don't exist in Poincaré, and they have an exponentially small tail near the boundary. So to do this ADS Rindler reconstruction physically, you're standing at the boundary, you have to measure these exponentially small tails.
Right.
So it's sort of at this level it's unclear if that's physical or not. But there's precisely analogous problem, which is consider an electromagnetic field inside of a waveguide, and then stand outside the waveguide, say a mile away. So mathematically you can still reconstruct the field inside because there are evanescent modes, precisely the same modes with omega less than k, which are exponentially decaying, which exist outside the waveguide. So you can stand a mile away and measure those and reconstruct it. And obviously we don't think that's physical, so that's precisely analogous to what's happening in Rindler. So I agree with Ben that this isn't really something you can physically do.
Physical is different from practical.
Yeah.
When you solve the Cauchy problem, you allow yourself perfect initial data. That's part of the closing the
No, but there, like in the normal time evolved Cauchy problem, there things are continuous. You know, if your initial data is close to zero, and you're solving in a wave equation with positive mass, then things will not blow up. Okay, so those. Whereas this doesn't have that property. And I can mention just a physical understanding of what can go wrong here. What can go wrong just at the level of solving classical differential equations. What can go wrong is you can have some kind of solution that basically just comes through here and it's localized near a null geodesic. You have these null geodesics that don't hit the part of the boundary we're looking at, but they do go through this Rindler wedge. Those are physically the things that are the problem, because at the classical level, you can make this arbitrarily well concentrated along this null geodesic. If you had the whole boundary, you would have no problem seeing this thing. Yeah, sorry, this drawing isn't very good. So it kind of goes to the back. It goes from the front side of the cylinder through the wedge to the back of the cylinder along this null ray.
But actually, can you make a solution like that literally dies at vanishes at the boundary, so it doesn't produce a signature that is picked up by this smearing function?
You can take a sequence of solutions at the classical level. You can make a sequence of solutions which continue to have order 1 bulk perturbation and have smaller and smaller boundary data. Okay?
So I think it's even simpler than that. I can give you a simple example of initial data. I can use the unique retarded minus advanced Green's function to construct the boundary data.
Retarded what?
The fundamental solution, the retarded minus advanced Green's function.
Oh, yeah.
Okay. And I can't. The simple example I will give you is a case where the HKLL smearing functions that exist in the literature can't reconstruct that solution. And the example is simply initial data in the Rindler wedge that is compactly supported. So initial data satisfies no equation of motion. It's really specifiable.
Initial data
on some space-like surface in the Rindler wedge.
In the Rindler wedge.
Okay. So I can choose a smooth, compactly supported set of initial data.
Let's say here.
Yep. And if you draw the future and past domain of influence of that initial data, you'll see that it hits the wedge on the boundary after some finite time. That means that the boundary data corresponding to this solution is clearly not analytic in position space.
Yeah.
And analyticity in position space is essentially what is required in order for it to converge against these HKLL Green's functions. So now
you can't build that out of the normalizable node.
Sure you can. It's clearly normalizable. It's
sorry, no.
Yeah. Okay. So my point is, take your favorite physical configuration, some solution in the bulk, and I can add to that solution my solution with an arbitrarily small coefficient, and you no longer can reconstruct it. Okay. So this is a problem purely in classical physics, but we can now extend the problem to a quantized Klein-Gordon field. By complete analogy to this, I can take your favorite 2-point function, which you can reconstruct, and I can add this solution so as to make it a new state in the bulk quantized theory.
Oh, sorry, is it, I guess, obvious that when you build this in terms of the normalizable modes, that you only, when you evolve forward, you only stay within the lifetime of the compact supporter?
You stay in the domain of influence because I'm using the unique retarded minus advanced Green's function. Yeah, with satisfying Dirichlet boundary conditions.
Momentum space reconstruction would fail for this? Is that what you said?
That's right. The formal objects that are written down as a classical physics problem, there's no reason. Let's see how it says. The K's written down as formal mode sums diverge very badly in momentum space, so you have to integrate them against something that balances that. It turns out that the correlation functions in the usual states we consider in a CFT do that. I'm just stating that the classical physics problem is actually not solved by HKLL. Right. And I don't think the story is over with that. I don't think there's a proof. There are arguments that you can't do better than HKLL, but I don't think that's true. So I agree with you that this is like a massive thing that still needs to be worked on.
Yeah. So, well, by the way, these are some of the experts on this topic, Vlad and Stefan and Ian. But I mean, the point is, there's all kinds of things that you could imagine will rescue this. So I said that ADS CFT lore tells you that this part of the boundary knows about this part of the bulk. But the lore didn't tell us that we can get away with these stupid objects. Okay? There's nothing in the lore about that. So one point of view is, and I think the point of view we advocated in our paper a while ago, was, yeah, this information about local stuff in the Rindler wedge really isn't contained in this local bulk data, in this local boundary data, and in fact it's contained in some other stuff, in some non-local operators that are in this right Rindler wedge. So there's something different that's happening between the global reconstruction, where in the global reconstruction there was no mixing between different orders in 1 over n or anything like that. In the global reconstruction, you could just reconstruct what was happening at point at the center using these simple low dimension operators in the CFT. And in the Rindler wedge, we still think for various reasons that it should work, but this information is really not contained in these local operators. Yeah.
I disagree with this interpretation because I'm simple-minded and I want to just focus on this classical field theory problem in the bulk.
Mm-hmm.
I'm not going to appeal to Wilson lines or anything. I'm just talking this classical field theory in the bulk, and what I've told you and what you've said is that okay, so there's a unique map from initial data on some surface in the bulk to the boundary, and all I'm claiming is that HKL has yet to construct a full inverse map. But you're trying to state something stronger, which is that the inverse map in this classical field theory problem doesn't exist. And I don't.
Well, I think it is a
counterexample. Certainly does not show that because you
right. I'm
just
just
map to zero data on the boundary. You just map to something with a formula.
I'm just saying that it doesn't pass my intuition from classical field theory that this problem, being not solved, cannot be solved.
Well, maybe make maybe draw a picture. Actually, sorry. I just this is some argument which
here.
Well,
I'm going to make one last comment, which is clearly with gravitational back reaction and so on, quantum mechanics, I can no longer do this thing. But then that's kind of mixing orders in 1 over n, right? That we didn't have to do in this global case. There's some kind of clue about what sort of operators are encoding this information.
So I'm not going to disagree with anything Ben said. I just want to present a paradox that I think illustrates it very nicely. So let's look at 2 overlapping diamonds in the boundary theory. Let's say these 2. And now let's imagine that, in fact, let's imagine that there was a well-defined sort of radial Cauchy problem in the bulk, so that if I completely specified the data in this diamond, then it would uniquely specify the solution inside of the causal wedge. And similarly, let's imagine it for this one. But then this is clearly false, right? Because these wedges in the bulk, they overlap, and there are points in the overlap which I can send a signal to from here. Okay, I can put a source here, a compactly supported source that is causally separated from the overlap of the wedges, but it doesn't change the initial data in this diamond at all. And so that's clearly a true fact about solutions of the wave equation in this geometry, and therefore there can't be a unique map from the boundary data here into the bulk. And so
if you know the sources in advance, why can't there be a unique map?
Because say I completely specify the source here to be 0, just to be something. Okay. Now if that uniquely determines the solution throughout the wedge here, that's bad because I can send a signal from here which changes that solution inside of the wedge.
But then you would have changed the boundary.
No, it doesn't. It doesn't. No. I'm not doing it in the CFT. I'm doing it at the level of I can put whatever function I want in the diamond here. So the resolution in the CFT is that it's impossible for me to put a compactly supported source here because CFT operators obey Heisenberg equation. So if I do something here, it sends a signal here. And without that effect, that's the only reason that there's this Rindler reconstruction has a chance of being correct in ADS CFT.
Your bulk source can't send a signal to your other boundary?
No, it sends a signal into the bulk, but remember, I'm allowed to specify arbitrary functional dependence both in time and space for the sources. Because we're trying to solve the PDE this way. Yeah. So I can put whatever source I want throughout here and throughout here. So my point is that I can just view the source as a function of this whole region here. And now there's a deformation of the source I can do where I just deform it in a compactly supported way here. And that doesn't change the source here at all by definition. Okay. It doesn't change the source in this diamond.
Does it change the boundary values?
No, it doesn't. That's the point.
That's the problem you're trying to set up.
But
You're saying you can't.
Daniel, your argument relies on not using the boundary Hamiltonian.
Yes, that's right, because I'm making a point about solving classical wave equations. From a classical wave equation point of view, you could just specify an arbitrary function here and look for a solution in the bulk, right?
That you
but
really can't do.
Well, yeah. So
I think these are two different issues. There's the fact that the boundary.
Well, so if there were a smearing function, if the smearing function were a function, this would be a contradiction.
No, only if the smearing function was guaranteed to give you a solution for all possible boundary data. Whereas
That's what I mean. So, but if it was, if the smearing function was,
only give you solutions that match the boundary data anyway, when the boundary data is something that actually is boundary data of a smooth bulk solution. There are some bits of data that you put in, and it just gives.
Well, you could imagine, right? You could imagine that you could integrate it against an arbitrary source here, and get some solution. And I guess what I'm saying is that this illustrates that you can't have that.
If the boundary limit of what you constructed, it does not match the boundary stuff you put in.
Well, because you're worried about what happened. You're worried about it becoming singular in the bulk somewhere, right? Sorry, it would have to be at the horizon or something. Okay, maybe this isn't helping. I thought this was the same.
Let me just say, I think this is related to the question I had about the systematic expansion, actually.
I think Don was saying in global coordinates you would have the same problem.
Well, in global coordinates, there's an issue with being normalizable at the horizon.
Global coordinates.
Sorry, in Poincare. In global, there's an issue with being regular in the center.
That's not the issue.
If you did something that's not good data, it may not converge.
No, so say that I didn't care about what was going on in the center. Then I wouldn't have this condition that omega is quantized for solutions in global coordinates. I could have modes that go to arbitrary spherical harmonics times arbitrary omega, and therefore I can have any boundary data that I want. So it's regularity in the center that constrains the boundary
That's
data.
true, and there are various ways you can try to do the reconstruction map. If you use HKLL's global Green's function, and you feed it arbitrary data, it is a smooth solution to a linearized wave equation, no matter what boundary data you feed it.
So the point I was making is that in the Rindler wedge, there's a complete set of modes that are normalizable, and whose boundary values are a complete set of modes in the Rindler wedge with arbitrary frequency and arbitrary momentum.
That's right.
Which means that I can expand an arbitrary source in the boundary in terms of those modes. Okay? So that sounds bad, right? Because this could happen. And so the reason why it's not bad is because the smearing functions are distributional. So that if I put in an arbitrary source made out of the allowed modes, then the integral won't make sense. So like if I put in this thing that's compactly supported in both space and time, and I try and integrate it against the distribution, then what I learned from Ian is that the distribution doesn't like this because it doesn't fall off fast enough at large space-like momentum. And so to me, that's the essence of why the Rindler smearing function must be a distribution.
Let me see. I think this is connected with the questions I had about the systematic expansion when you want to work order by order in G. So say there was this simple model that box phi is equal to G phi squared. And you could write down using this HKLL, HMPS construction that phi of x is equal to integral over the boundary, k of x b, the smearing function, O of b, plus integral over the bulk of the space-like Green's function, and then phi squared of x prime. And there's a g here. And so if you're thinking about it in the global context, then if you put in here something that satisfies the actual equation with g phi squared, then you'll end up constructing something non-normalizable with the smearing function. And actually, I think if you did this likewise in the Rindler case, you'd end up with these same other kinds of problems. Since you're sourcing this or smearing
with K something that doesn't satisfy the free wave equation, then you're ending up with the kind of thing that has the bad, well, either non-normalizable boundary behavior, or presumably in the Rindler context, it would be in the category of data that doesn't lead to a nice smooth bulk solution at the free level. And so, just thinking about the global case, here you have something non-normalizable. Here you have something non-normalizable. This is supposed to be normalizable, and that's why you have a challenge with at least systematically organizing the expansion as an expansion in a small parameter. Now, people say, well, we can reorganize it, but I think it's a related set of questions.
I think for that, a solution is to build a K that only involves normalizable nodes in the bulk. Right?
Well, again, the question is which K, which K exactly? And we had part of this discussion over lunch. So you mean not the one that comes from the space-like?
That's right.
But, well, yeah, is...
The Poincare one is an example of one that's like that. So if we just decide to discuss the Poincare patch, then that removes all the ambiguity in the smearing function, and it's normalizable.
Okay, but we just said that, I think you just said that the Poincare smearing function doesn't accept arbitrary data without doing something bad at the horizon. Isn't that?
The Poincare wants this omega squared greater than k squared.
Right. So if,
But it is a good function.
Yeah, but if you don't satisfy this condition, omega squared bigger than k squared, then what happens at the Poincare horizon?
Well, it's written as an integral momentum space with support only in the good region. So if you feed it anything in the bad region, it just doesn't see it.
Or it just kills it. Okay. Then so maybe that takes care of it. I guess I'd like to see that.
The first one is that there's a way in which this looks trivial, which is I guess the way that Banks, Douglas, Horowitz, Martin did, which is you canonically quantize the bulk field, so you expand the bulk field in terms of normal modes, and then you just use the extrapolate dictionary and this special property that the boundary limit of the normal modes is orthonormal over space and time, so that you can interpret the creation operators as the Fourier transform of O. And so that's it, you're done.
That only works with, G equals 0, or, I'm thinking of G as 1 over n, basically. I could put in the n, too.
You can keep using you can keep working in Fourier space if you like and correcting this way. So that was my first comment. It makes things look pleasant. The second comment was, between those two equations, you can just write Green's theorem, which is an identity.
This came from Green's theorem, actually.
I know, that's why I mean in between those, the first and second, there's a step where you use Green's theorem, which is an identity.
Good, yes, this is an identity, in fact, at this stage.
So the left-hand side is well defined by assumptions, so the right-hand side must be too.
Yeah, no, but the point is that, for example, if you look at HKLL or HMPS, they try to give this as an explanation of how you can take your boundary data and order by order reconstruct the bulk operator, order by order in G over n, where it's an expansion where you have a dominant term, a smaller term, like in QED or other perturbative expansions. And the point being that if you actually try that in practice according to this scheme, then since you're plugging in here an O, which is coming from a solution of this equation, not the free equation, this will construct something non-normalizable, at least with the space-like.
Just don't use the space. I mean,
well, okay, but that was the one they started with. So, okay, so maybe there's another one.
A lot of work because you wanted a space. If you just write K as a sum over mode, I mean,
the space-like is written as a sum over mode. So, actually.
What did I say that was fun? There were reasons one wanted the space-like.
Go ahead.
Sorry, I'm just back. This K, if I could just write, it's not.
But which K do you want? I guess. Well, that's a. What's the alternative K you're going to?
So this is a bulk point. This is a boundary point. This is a bulk normal mode, and this is the boundary point.
Okay, so this is the Poincare version.
No, this is global pump.
Okay. Yeah, but can't this K in particular, their space-like one, be written that way?
So Kabat and collaborators, they took this thing, and then they added a bunch of stuff to it, which satisfies the wave equation.
Yeah, so it also can be written in that fashion. So it's not just a question.
This is manifestly normalizable because if you take the boundary, because if you take the bulk point to the boundary, you just have this guy and this fall.
The kind of thing that can happen is the sum cannot converge when you go to the boundary. An example is the bulk boundary propagator, which is, I think, if I recall properly, can be expanded in terms of the normalizable wave functions.
Non-normalized.
No, it can be expanded in terms of the normalizable ones. The bulk boundary propagator. We'll get to that. Let me tell you how you know this. You know this because the bulk boundary propagator can be written in terms of the Feynman propagator, which also can be likewise expanded.
No, the Feynman propagator is expanded in terms of normalizable modes.
Yeah, right. That's okay. So the
bulk boundary propagator is some limit of the bulk propagator.
Yeah. So
the bulk propagator involves normalizable modes.
Okay. So the bulk boundary propagator can be expanded in terms of normalizable modes. Agreed? Okay. But we know that the bulk boundary propagator is non-normalizable exactly when you have a boundary point here and the bulk point goes to there. It's non-normal. It has non-normalizable behavior at that point. And what's going on is that basically the series is not converging.
Yeah, it's like secretly short. It's secretly somehow the short distance part of the bulk propagator.
Something. Yeah. So and I think the same thing. So you have to be careful about that kind of argument with this kind of sum. I think in other cases too.
The source that's being used on the right-hand side, that's a phi squared, so it's falling off very rapidly with C.
That is not the key point, though. The key point is that the only thing that K accepts and gives you back a normalizable solution is something that comes from a free solution. It's not just that it dies near the boundary. It only accepts things that are free. That's what the earlier discussion was. And
I don't understand. I mean, that equation is just a mathematical identity.
I agree. Yeah, so good. So it's a mathematical identity, and so it's fine as an identity, but the point is if we want to now use it to approximate, namely we're going to take this phi is this plus g times that, and then we plug it back in. We put the phi back into here, phi squared, and then we write it as g times smearing function times O squared, and then plus higher order terms. So we're trying to write an order by order expansion in G. The point is that's not an expansion where we have a leading term plus smaller, etc., because the leading term actually has a big non-normalizable contribution. And we know that must be canceled by the subleading terms because this is going to be normalizable in the end.
G to 0.
None of this happens at G equals 0.
So
the question is for a perturbative
G to 0, and then you just have KO, and that's the final thing.
No, but he's saying the first term is one of our interactions which are non-normalizable. We cancel the second term.
Yeah, so in other words, they're large. So you don't have something that's a leading expression plus a subleading expression. You have big minus big equals correct answer, which is small. That's the systematics of the expansion.
You can avoid all of that just by using a K that only involves normalizable solutions that have omega squared bigger than K squared.
Right.
Then the issue goes away.
We're stuck in some kind of closed timeline curve.
Say something.
Yeah, sure.
We're discussing this bulk reconstruction, right? Now, and we're discussing constructing these operators which are small perturbations around the bulk. Wouldn't it be nice to be able to reconstruct the metric somehow directly the background? So from the finding what in the field theory is the zeroth order thing, the classical thing, the metric, the background. I think that would be nice. And there are some other examples where you can do something like this. So the example are, for example, matrix models where you can start from, let's say, a matrix integral is a simple example, where you start from the matrix integral, and So let's say you have an integral of some matrix, a single matrix of this kind, and we know that in the large n limit there is some kind of saddle point approximation. So something becomes classical. This is analogous to the metric, the background that becomes classical in the bulk of ADS, and that something in this case can be understood, and that something is the eigenvalue distribution of these matrices. So this can be approximated as, let's say, some integral over, let's say, eigenvalue distributions of some classical action, which is a functional of the eigenvalue distribution. And then there is a saddle point for that eigenvalue distribution, some particular shape for this eigenvalue distribution. And that seems analogous to the shape in the metric. So it would be nice if one could find that the metric is analogous to this rho of lambda. And in many senses, this looks like a reasonable thing. So in this case, there is some geometry behind this rho of lambda and so on. So maybe we're somehow missing the big thing, which is the thing that becomes classical, and finding the saddle point, this object in the boundary theory. Exercise.
So I guess. But in any case, you'd find something that was classical in the 1 over n sense.
Right. I mean, this eigenvalue distribution is subtle. It's not because the eigenvalues themselves. So it's not a subtle point for the eigenvalues. So you need to take a group of eigenvalues, and only when you group them, it becomes something classical. So each eigenvalue fluctuates a lot, and then they make a classical distribution. So one.
So in n equals 4 super Young-Mills theory, do we not have any sense of what the saddle is?
Yeah, it is.
I mean,
well, we know the answer. We know we would like to get the metric and so on, but we don't know.
But just from the field theory point of view.
No.
Well, no, we don't. At weak coupling, it's basically the same as what you said, right? Like the eigenvalues.
Right. So if you took
what that turns into.
Some very simple example. So there is, I don't know, you look at the half EPS sector and so on, then you reduce to a matrix model, you can do this thing, but it's not something that is valid for the whole thing.
I mean, I just remember.
That's equivalent really to solving the theory.
Yeah, well, that may make you think you won't be able to do it, but perhaps there is the right average that one could argue obeys these equations, obeys the classical equations, and if we understand what this average is.
I just remember some review that was written in the 1960s or something in Migdal, and some people were trying to write these equations, right? It was.
Yeah, loop equations. Yeah, that's.
Yeah. So.
Well, those were equations for Wilson loops, for Wilson loop observables. And if you wish, the modern version of loop equations are these integrability constraints on Wilson loops. But well,
Well, so there you do kind of see the classical strain equation somehow coming out of some
directly, yeah. But again, it's the perturbation around the background. We don't see very clearly the background.
You don't see the classical string equations in ADS.
We did.
You do?
You missed an eigenvalue discussion.
Got large lambda?
No, not from loop equation.
From integrability?
Even from integrability, you only see the final answer. You constrain the final answer.
Do you have a comment?
Yeah, we know that in the bulk you can make a classical field configuration through lots of T-channel iconization of the field. So maybe one would look for the boundary dual of that, summing up all the T-channel exchanges.
Wasn't there just a paper about that by Liam and right?
Is that right?
Yeah.
I must have read it subconsciously. Anyway, does that answer your question? Okay, so that's the answer.
So I guess we're gonna simplify. So we can have either the vacuum or a black hole, and then I think you're just trying to ask what do we do in the CFT to figure out what the classical?
To read off what the classical metric is. Even the vacuum metric. So all we do normally in ADS is relies on the symmetries. We match the symmetries, and then we look at small perturbations to transform non-trivially into the symmetry. I just think about the case which doesn't have conformity, maybe that's sharper. So think about that. So, and then how do you describe that metric?
Should that question have an answer? I mean, if you're going to talk about the bulk geometry, do you need to say what kind of probe you're using?
Well, in the large coupling limit, it presumably has an answer. Maybe there are different variables you can use. There's reparametrization symmetry, of course. Expect to have an answer. I mean, and another is hydrodynamics, right? So you have all the particles and so on, and you can define the hydrodynamical variable, and there is a certain degree of freedom in how you define it. Well, we more or less understand what it is the density. It's a reduction in the number of degrees of freedom that you need to describe the theory. So naively, if you have the Boltzmann equation, you have both functions of P and R, and then in hydrodynamics you go to just functions of R. So that's kind of analogous to taking all the operators you could have, all the variables you could have in the boundary theorem, reducing to just the metric, few number of fields. So analogous.
You're not happy with taking Dan's order 1/n expansion and then taking the expectation value of the metric and resumming some infinite class of diagrams to see that the background shifted?
Not completely happy. I mean, I agree this is a possible solution, but
it's not an integration variable. So that's what you want, right?
Yeah, that's right. I mean, that discussion of the matrix model looks different in spirit. It would be nice to have something similar.
I think Sungsik Lee has something that's more like this. Aristotle, understand it well, some split of the path integral CFT into the sort of single trace and the rest. There he tries to get a saddle point approximation, which is a very nice explanation. Do you remember that? He gave this talk.
Yeah. I mean, he does an integral transform between the O's and the J's as you want the sources.
Right.
The metric is one of the sources, so he tries to transform the path integral from 1 over the usual degrees of freedom to 1 over the sources, and that gives the metric.
Which method?
Just the field theory path integral.
In the vector-like case,
in the vector-like case,
sort of
another example.
You can do
exactly,
something like this, right?
It's
what's called a master field.
Yeah, I mean, I think what he does is true. It's just how maybe not.
Well, it's non-trivial in general because you get the full string theory, right? You get the string field theory, and then it's the classical. So that's what it should be in general, and then maybe it simplifies in the strong cover.
Well, people should feel free to trickle out. I actually have another question for Dan, which maybe. Did you really explain to us the simplest case where we see where you go? Well, let's back up. You didn't have an issue with the free field construction with the code subspace, going outside of it. But what's the simplest case where you go outside of the code subspace? Do you have to actually make a black hole, or you had promised in your talk that you were going to give sort of simple examples?
Well, I just meant the big black hole.
You meant the big black hole.
Yeah, I think. Well, the code subspace is not unique, so you. Yeah, I think to sort of seriously get into trouble, you need to have a big. I mean, well, actually, you can have a small black hole. Yeah, a small black hole would also work, but they're harder to describe. But
so So it's not something simple like some high energy modes.
No, I think some gravitons zipping around at high energies near the boundary is fine.
Okay. Any other questions or discussion?